Okay, so at the moment when we play our game, our character is in his idle animation, and when we add input, we cause our character to move, and he goes into his running animation. This is due to the fact that our state machine is now aware of our character's movement speed. It toggles between the idle and running states depending on the character's movement. However, we want it to make it so the character will blend between the different running animations we have depending on our character's movement direction. To do this, we're going to be creating a blend space. A blend space is an animation asset in Unreal that we can use to blend between multiple different animations. Blend spaces have their own axis values, which are used to control how we blend between the animations of the blend space. Let's take a look. To create a blend space, let's find the folder where we have our marine animations. And let's right click in this folder and come to animation. And here we can see the animation assets we can create. One of them is a blend space. We also see a blend space 1D here. When we hover over a blend space, it says it contains a grid of data points with weights from sample points in the space. So it's a bit of a complex explanation for this. Let's just create a regular blend space here and take a look at it. First, we have to pick a skeleton that we want the blend space to be associated with. We want it to be associated with the marine skeleton. So what do we want to call the blend space? Well, let's just call this movement blend space. And let's double click on the asset to open it. Here's our first look at a blend space. We see along the bottom center of the interface, we have this graph. And this graph has a vertical axis and a horizontal axis that we plot animations on. In our case, the vertical axis is going to be our character movement speed, and the horizontal axis is going to be the character's movement direction. When we plot animations onto the graph, we're going to be able to see how the animations will blend depending on the character's speed and the character's movement direction. All of this will be driven by variables inside our state machine. All we have to focus on here is setting up our axis values and plotting our animations onto this graph. So how do we customize the horizontal axis and the vertical axis? Well, if we look on the Asset Details panel, we see we have the axis settings, and we can expand each axis for more details here. We can see we can provide the axis name and the minimum axis value and also the maximum axis value. So for the horizontal axis, the name is going to be movement direction. For the vertical axis, the name is going to be movement speed. And we can see that the axis names have been updated on the graph after we hit enter. Our movement speed is going to go between 0 and the maximum movement speed of our character, which is the max walk speed on the character movement component. So for me, that's going to be 600. And our movement direction is going to go between negative 180 to positive 180. Okay, now that's our axis values set up. We can see they are named correctly and they have their value ranges applied. Now we just need to plot our animations onto the graph. We can drag and drop animations onto the graph from the asset browser. But what animations do we want to use here, and where do we plot them onto the graph? Well, let's look at the value ranges. 0 movement direction and 0 movement speed is going to be plotted here. So what happens if we're not moving and we're not moving in any direction? Well, we should be playing the idle animation. So let's click and drag the idle animation and drag it onto the bottom of the graph here. Now what happens if our movement speed is 0 and the movement direction is 90 degrees? Well, we're still going to be in the idle animation because we have 0 movement speed. In fact, the whole bottom section of this graph represents our movement speed being 0, so we're going to plot our idle animation all along the bottom here. Now the top of our graph represents our character moving, so if we are moving and we are moving at 0 degrees, we should be running forwards. But if we are moving and we are moving at 90 degrees, we could be using the run right animation. And if we are running at negative 90 degrees, we could be running left. And if we are running at 180 degrees or negative 180 degrees, this will both be the run backward animation, so we can plot these here as well. Now we can preview our blend space by holding down the left shift key and dragging our mouse around. So all along the bottom is where we are idle, but if we start moving, we can see how we would blend to our run forwards animation. And then if we started to change our movement direction to 90 degrees, we would see that the animation would blend to the running right animation. And we can see how this would work for all the different movement direction values. Okay, so this is how our blend space is going to work, and we're going to drive these values here with some variables in our animation blueprint. So let's save this asset and let's close it, and let's come back to our animation blueprint. The first thing we want to do is make sure that we're calculating the movement direction of the player character. Now this sounds a bit scary, but it's quite simple to do because Unreal already has a function for this. So make sure you're inside the event graph, and just to let you know, if you accidentally close the event graph or the anim graph, you can double click on either one inside the My Blueprint tab to bring them back. So inside the event graph, to calculate the direction of the player's movement, we can right click and we can come to animation, and the first function here is called calculate direction. We can hook this up to the execution flow, and we can see that we have two inputs here, velocity and base rotation. Well, we're already getting the velocity here, so let's click and drag from the return value and plug it in to the calculate direction. And now for the base rotation, we can simply use the actor rotation of our marine. So let's drag out from the pin from the cast and get the actor rotation. And we can use the return value from this for our base rotation. Now we need to store this direction just like we do when we calculate the movement speed. So let's right click on the return value here and promote it to a variable named movement direction. Okay, and that is our movement direction calculated. Now our blueprint is looking a tiny bit messy here, so let's take a look at cleaning this up. Instead of getting the pawn owner and casting to our marine every frame, we're going to store a reference to our marine from the begin play event. So in an empty space, let's right click and come to add event, and let's select the event blueprint begin play. And let's duplicate the try get pawn owner and the cast up to our begin play event. So on begin play, we get the pawn owner and check to see if it's our marine. Now what can we do with this? Well, we can promote the reference pin to a variable, and we can just call this marine. Now this allows us to remove our try get pawn owner and cast to the marine off the tick here, and we can grab our marine and throw it into the target for the get velocity, and we can grab it again and throw it into the target for the get actor rotation. And we can space these nodes out a bit to show that they are doing two different things here, and we can even break the velocity link and call get velocity on this instance of our variable. So this is our calculate movement direction, and this is our calculate movement speed. Now it's important to note that when dealing with references to actors, you have to check if they are valid, or sometimes you'll play and then when you stop playing you'll see some errors pop up saying that the reference isn't valid. This is because the reference might not be set. So to fix this, we first want to get our marine, and we want to check if it's valid, and we can do this by calling the isValid macro. So every frame we'll check to see if the marine is valid, and if he is valid we'll calculate his movement speed, and then we will calculate the movement direction. And right now I just want you to pause here to collapse your code into functions where you calculate your movement speed and your movement direction. Okay, so we can start by collapsing our calculate movement speed down into a function, and we can simply call it the same name, calculate movement speed. And let's move that over there. And then with our calculate direction, we can right click on this and collapse this to a function called calculate movement direction. And we can bring this over here as well. And we can get rid of these errors just by hitting compile. It's always important to take your time to write clean, readable blueprint code. It's a good habit to get into early on. If you come back to this code later, or if we start to add more to it at any time, we'll be able to clearly understand what does what. It's so easy to just say, oh, I'll just clean this up later and then never do it. But let's always make sure that we make our code clean and readable first before moving on to something else. Now we calculate our movement speed and we calculate our movement direction that can be used for our blend space. So let's switch over to our anim graph and let's enter our locomotion state machine. And we're going to change our states here. Our idle state is going to become the single state for our movement blend space. To rename it, we can select it and we can hit F2 to rename. And we're not even going to need our running state, but we will be adding another state later in this course when we set up our sprint ability. But with our movement blend space, we can enter the state And instead of it playing idle, we can remove this. We can come to our asset browser and we can see we have our movement blend space here. We can click and drag it onto the graph and we can hook it up to the result. And look, we have some input pins for our movement direction and movement speed. These are the horizontal axis and the vertical axis that we set up. So let's connect our movement speed to the input here, and the same for the movement direction. So our variables are going to be driving the axis values of our blend space now. So let's hit compile and save and close our animation blueprint and come and play the game and see what happens now. So we're in our idle animation. And if we start moving in different directions, we can see that the animations are changing depending on our movement direction. So our blend space is now working correctly. So this is really good progress. We have our character class moving and we have the mesh animating and responding to our movement. The next step for our character is to get him to turn. We're going to make the character turn towards the direction that we want him to fire. So we're going to start working on this in the next lesson. So we want to start setting up the aiming for our character, and in this section we're going to be setting up both mouse aiming and thumbstick aiming for gamepads. We're going to start with the thumbstick aiming. I've got my gamepad plugged in and I can hit play and move my character around with the left thumbstick because we bound the left thumbstick to our input axis mapping for moving forwards and moving right. But when we turn the right thumbstick, we're going to make the character face the direction that we're turning our thumbstick in. So to begin with this, we're going to create some axis mappings for our thumbstick aiming. So let's come up to Edit, and then Project Settings. And let's come to the Input section so we can add in two new axis mappings. The first is going to be called Thumbstick Aim Up, and the second is going to be called Thumbstick Aim Right. For the thumbstick aim up, we're going to bind the gamepad right thumbstick y-axis for this. So that's going to be moving the thumbstick up and down. And for moving the thumbstick right and left, we're going to bind this to the thumbstick aim right axis mapping, which is going to be gamepad right thumbstick x-axis. Okay, so this is our input mapping setup for the gamepad. Let's close the project settings and come back to our marine blueprint. So how are we going to translate the right thumbstick into actually rotating our character? Well, we're going to start writing a function that's going to be executed from our tick event. Let's create a new function called update player aim. Let's come back to our event graph and make sure that we execute this from our tick event. Now let's double click on our function so we can start writing some blueprints code for it. First, we must understand that the player controller has its own rotation that the pawn will listen to by default for aiming and rotating. What do I mean by this? Well, if we select the Class Defaults button on the top toolbar, we can see on the Details panel we have this pawn section, and here it's telling us that by default it's going to use the controller rotation yaw. So what does this mean? If we hover over this, it says if true, this pawn's yaw will be updated to match the controller's control rotation yaw if controlled by a player controller. The player controller has its own rotator in its class called control rotation. This control rotation is used by pawns for dealing with things such as rotating and aiming. So to rotate our character, we're going to want to affect the control rotation of the player controller. So inside our update player aim function, we're going to get the player controller and we're going to set the control rotation of the player controller. To do this, we're going to drag out from the return value and call the set control rotation function. We're going to hook this up to the execution pin, and here we have a new rotation. So we have this rotator pin. We're going to drag this out and just type in make rotator. So now we have access to the roll, pitch, and yaw values. And remember, the pitch and the roll aren't checked on the class defaults. So by default, our character is going to ignore the roll and pitch values. But this is fine because we only care about the yaw. The yaw will turn our player character. For now, let's just hard code the yaw in as 135 for now. This should mean that when we play the game, our character will be rotated by 135 degrees. So let's try this. Let's come back to our level and hit play. So we can actually see that our character has rotated now, but we have an issue here. The character is rotating, but so is the camera as well. We don't want the camera to rotate when the character rotates, and I want you to try and fix this now. Pause here and stop our camera from rotating whenever we rotate the character. Don't worry if you can't remember exactly how to do this, I'll show you again in a moment, but pause here and see if you can remember. So to fix our camera from rotating when the character rotates, we want to be looking towards the components of our marine blueprint. It's all because of our spring arm. Our spring arm is always going to try maintain its relative rotation to the root component. So when the character rotates, the spring arm rotates with it. But we can override this by selecting the spring arm, and on the details panel where we have the transform section, we can drop down rotation, and we can see here that it's set to use relative rotation, but we can change this to world rotation, so the spring arm will completely ignore the rotation of our character. Now if we come back to our level and hit play, we can see our character is rotated by 135 degrees, but the camera hasn't rotated with it. Awesome. Now there's something we should make ourselves aware of here. Our camera is always going to be facing along the x-axis of our level, and the same goes for our movement. If we push up on the thumbstick or press W, the character will move positively along the x-axis. Just be aware of this if you go off and design any levels. If you rotate your player start, the controls might seem a bit funky, but you can always use this little widget in our viewport showing us the directions for each axis, and we can visualize here which is the forward facing direction of our level by looking at the X direction. Now let's come back to our marine blueprint and back to our update player aim function so we can continue setting up our thumbstick aim. I'm just going to move our nodes along here just so we can make a bit more space to write our code. So we're going to start by getting our thumbstick aim axis values, so thumbstick aim up, and we're also going to get thumbstick aim right. Now before moving any further, let's visualize what we're going to be doing here. When we push the right thumbstick up or down, our aim up axis value is going to be between the range of -1 and 1. And if we push the thumbstick right or left, our aim right axis value is going to be between the range of -1 and 1 as well. We somehow need to convert these values to an angle, so we can use it as the yaw value for setting our control rotation. Now we're not going to be diving really deep into the math behind this, but to help us convert our axis values to an angle, we're going to use a function called atan 2 degrees. This function is going to return the arc tangent of the two numbers we provide, and the results we get from this function will be an angle. Imagine we've just pushed the right thumbstick diagonally up to the right. The axis values for aim up and aim right would both be 0.5. If we pass these into the atan 2 degrees function, we would get the result we need as an angle. Let's just start printing out these values of this function to our screen so we can see how our input affects it. Let's right click and search for atan. We can see different functions here. We're going to use the one named atan 2 degrees. So we can plug our thumbstick aim up into the A input, and then we can plug the thumbstick aim right into the B input. Now instead of plugging this straight into our make rotator node, we're going to print these values so we can see what's happening. So let's call the print string function, and let's make sure we hook up the execution pins here, and let's print out the return value of our atan 2 degrees function. Now let's come back to our level and hit play. So without pushing the thumbstick, we get 0. Okay, but if we start pushing the thumbstick up, it's giving us a value of -90. As we start to move the thumbstick towards the right, we get 0. And when we push it down, we get 90. And then when we push it left, we get 180. So let's just visualize this quickly. So currently, up is -90 degrees and down is 90 degrees. Right is 0 degrees and left is 180 degrees. It's actually almost there. This is very close. It's just our A and B inputs need to be reversed for us on the atan 2 function. To fix this, let's use aim right as the A input and aim up as the B input. So now let's see what happens. When we push up, we get 180, and when we push right, we get 90 now, which is actually correct. When we push down, we get 0, and when we push left, we get negative 90, which is also correct, which is what we want. But 180 and 0 for pushing it up and down is wrong. This is because these are inverted. We just need to invert our scale value for our aim up input axis mapping. So now if we play the game and push up, we get 0 degrees, which is correct. We get 90 for right, we get 180 for down, and we get negative 90 for left. So this is actually looking really good. Let's come back to our function, and let's connect the return value now directly into the yaw input of the make rotator. Let's compile and save for the final time for this lesson, and let's try again. Now if we turn, we can see our character is facing the direction that we push our thumbstick in. Awesome, so this is working really well, and we can even run around the level and push the thumbstick and the character will still face towards the direction that we're looking in, independent of our movement. But we do have an issue here. You'll notice that if you release the thumbstick, your character will snap back up to 0 degrees. It will snap back up to aiming forwards. So we're going to be fixing this up in the next lesson by creating a thumbstick dead zone. So once you're ready, I'll see you in the next lesson.